Welcome back to the second video in our little series on complex numbers. In the first video on complex numbers, we looked at the algebraic picture. And indeed, I had a definition of a complex number as a symbol a plus ib. And indeed, we also had defined an addition and a multiplication algebraically on complex numbers. So addition was just sort of defined component-wise. It added the real components and it added the imaginary components. But multiplication was a little bit more of a complicated formula when you distributed out the multiplication. So now what I want to turn to is, well, what does all of this look like geometrically? Is there a way I can visualize this? What actually is multiplication of two complex numbers? How can I see the effect that that has? That's the goal of this video. So to look at the geometry, I want to actually just look at the normal old real number line, a single horizontal line where you put 0, 1, 2, 3, and so on as sort of markers along that line. But now what I'm going to do is take a two-dimensional picture here. I'm going to add a y-axis, if you will. But notice what I do. The y-axis is labeled I, 2i, minus 2i, and so forth. That is, I sort of want to imagine that my vertical axis is an imaginary axis. It's a way to store the imaginary components of a particular number. So consider, for example, 2 plus I. 2 plus I is a complex number. Real component 2, imaginary component 1. So there's an I in front of the component of 1. Then a way that I can represent 2 plus I graphically here is to, well, give myself a little line segment or a little arrow or a little point that occurs at the spot where I've taken 2 steps to the right along the real axis and 1 step up along the imaginary axis. 2 plus I is a coordinate in this two-dimensional coordinate system. So this is just a way to encode the data that's been given to us when you state 2 plus I. Okay, that's one. Let me do another one. This is minus 1 plus I, and the way I think about this is the real component is minus 1, so I take 1 step to the left, and then the imaginary component is also 1, and so I take 1 step up in the imaginary direction. Okay, that was interesting, but how do I now visualize addition? So let me add these two numbers, 2 plus I and minus 1 plus I. If I only knew the algebraic picture from the previous video, you add the real components and the imaginary components. 2 plus minus 1 adds up to 1, and I plus I adds up to 2i. Okay, so then where is this 1 plus 2i graphically? Well, it's just right up here. And this 1 plus 2i should not be thought of as completely random. Imagine you go down the little yellow line segment first and then went in the direction of the red. As in, imagine I sort of move the red over here. Notice how if you put them together in what they call a tip-to-tail method, that taking the yellow and the red successively adds up to, well, to the green, adds up to this 1 plus 2i. Indeed, if you want to manipulate the other way around and do the red one first and then the yellow, it also leads to the same spot. This is the commutativity property. It says it doesn't matter which order you do your addition of complex numbers. If you've seen linear algebra or vectors before, you'll notice that we have a very similar property for vector addition as well. Indeed, complex numbers at the level of just addition is indistinguishable from vector addition in 2 dimensions as well. Nevertheless, we have this picture. Okay, well, what about multiplication? Because even if you do know linear algebra and you're happy with vector addition, this picture is old hat to you. There isn't a multiplication of 2 vectors in R2 that we know from linear algebra to help motivate us. So let's try to figure out what's going on, because this multiplicative structure is really what separates complex numbers away from just being, well, a 2-dimensional Cartesian coordinate system. It's the fact that it's 2-dimensional Cartesian coordinate system with the ability to multiply that really gives you the complex numbers. Okay, so, well, let's try this. 2 plus I multiplied by I. So I've put the 2 points up here. I've got the yellow, which is I, which is just stepping 1 up, and then 2 plus I, which is 2 to the right and 1 up. Now, if I just multiply them algebraically, well, what do I get? The 2i goes together, and then the I squared becomes a minus 1, so minus 1 plus 2i. If I put that on the graph, well, it looks over here. Now, I want you to notice something. The red 2 plus I and the yellow minus 1 plus 2i have a 90-degree angle between them. Okay, so it's got a 90-degree angle. Why is that interesting? Well, this is actually the second time it's happened, because if you think about just I itself, well, I is 1 times I, And 1 lives on the horizontal and I lives on the imaginary, so multiplying 1 to I also means that it's 90 degrees rotated. These two vectors also have the same length. This really is just a 90-degree rotation of the one vector to the other. So that leads me to the question, is multiplying by I always a 90-degree rotation? All right, so I've actually just zoomed in a little bit here, so I'm going from sort of -1 to 1 and minus I to I. I'm going to draw a unit circle. So this is the circle of radius 1 drawing in the so-called complex plane. Let me put some point on that circle. And I'm now asking, well, how can I deal with complex numbers who live on the unit circle in this complex plane? We, of course, have studied these kind of unit circles with trigonometry for a long time, and so I can drop down a little triangle, I can put in an angle of alpha, and then the projection onto the horizontal is the definition of cosine of alpha, and the projection onto the vertical is the definition of sine of alpha. Okay, so this is kind of interesting. That is, really what I'm talking about is complex numbers of the form cosine of alpha plus I sine of alpha. So I want to sort of focus just on those complex numbers that have that real component of cosine and that imaginary component of sine of alpha. Let me put another one up there. Let me put an angle of beta, but still on that unit circle. So I've got two different complex numbers, the one with angle alpha, the one with angle beta. And I want to try to multiply them. So I'm trying to multiply this thing down here. Oh, okay, so let me focus just on this. Well, I'll distribute out that multiplication and I get this long expression. It's got a real component and it's got an imaginary component. And you might recognize the pattern of the coses and the sines. This is a trig law, a law that would have been proven back in any sort of normal trigonometry course. Indeed, the real component, that combination of cosines and sines, is nothing but cosine of alpha plus beta. And likewise for the imaginary component, this is sine of alpha plus beta. So here's the point. When you take the complex number defined by angle alpha and the one defined by angle beta and you multiply them, you end up with the complex number on the unit circle that is angle alpha plus beta. What this looks like here is this relatively nice picture where I've got the one which is the angle alpha, the other the angle beta. When you multiply them out, they're going to give the blue, which is another complex number with angle alpha plus beta. So this is really interesting. What that means is that for complex numbers, at least those on the unit circle so far, multiplying them two together is just rotating around this unit circle. So complex numbers are intimately connected with the idea of just rotation. That's our big takeaway. So in other words, rotation by theta is cosine of theta plus I sine of theta. A specific value you may care about is theta equal to pi over 2. You plug pi over 2 in, well, cosine of pi over 2 is 0, sine of pi over 2 is 1, so the complex number on the unit circle that represents rotation by pi over 2 is I. So that's what I is, rotation by pi over 2 in the complex plane. Okay, that was multiplying by I. What about multiplying by 2 now? So I'll take 1 plus I, I'll multiply it by the number 2. 2 can be located on the horizontal axis. Well, what this does algebraically is just, well, makes 1 plus I become 2 plus 2I. 2 plus 2I, graphically, is just taking the 1 plus I and stretching its length out. So multiplying by a real number here is just going to stretch the value of the complex number. It's taking where you originally were and stretching it. So multiplying by I was rotation, multiplying by a real number is stretching. So finally, let's put the two of them together. I'm considering a sort of generic point here. So its radius is no longer fixed to be 1, it's just some other circle. But nevertheless, it does going to have a radius of the circle of r, and then r cosine and r sine are sort of the real and the imaginary components of it. That is, what I get is a complex number z, which is r cosine plus ri sine theta. I can maybe factor the r out the front just to make it equal to the value of r times cosine of theta plus I sine of theta. And then the real point here is that when I look at this is my generic complex number. It can be written as this r factor out the front, this real number r, which is just a stretching factor. And then this cosine theta plus I sine of theta, which we've just seen is a rotation by theta. So the final takeaway here is that when you multiply by a complex number, you're doing one of two things. You're doing some amount of stretching, and you're doing some amount of rotating. That's what multiplying by a complex number visually does.